you've learned about ring tactic and linearity tactic and linearity maybe, and these are quite powerful. You've seen them in action, but here is sometimes they don't do the job for us, and you want something more powerful. So I should say this: what I'm going to explain to you is based on this tutorial by Heather Macbeth. So I finished the port to Lean 4 of her tutorial, and essentially everything I will say is taken from that, just to clarify. So let's go with examples. Here is an example of something you would maybe want to prove. Suppose you have A and B complex numbers, and you want to show, you're assuming that B plus 2 is 3. Sorry, you want to show if here is the hypothesis. It's visible. Suppose that A minus 5B is 4, and that B plus 2 is this is too large still. Hopefully that's still visible in the back. Yeah. Okay, so suppose that B plus 2 is 3, then you would like to show that A is 9, and this is a calc proof of how you could do it. You start with, you already seen the calc structure. That's how you would do it in, I guess, maybe in paper. You substitute, so you write A as A minus 5B plus 5B, right? That's you can prove by ring, and then 5B, you know that A minus 5B is 4. So here you have 4 A minus 5B in there. So by a rewrite, you can change it to this, and then another ring allows ring application allows you to factor out the B plus 2 out, because you have this other hypothesis telling you what B plus 2 is. So you factor this out, then you replace again into a 3, and then you clear it out and you get 9. So that would be the calculation you would do maybe by hand by using these two hypotheses. And so you keep intercalating, alternating between ring applications and rewrites, right? As you see here in the structure. Now you'd say, well, but this is something that linearity would do. So here's the same example, but now A and B are real numbers, say, and linearity just does it. So if I click here, you can see that this has no errors. Yeah, so the problem is that this works because R is a linearly ordered field, but for the complex numbers, that same proof, if I change this into a C, that stops working. Linearity won't know how to deal with complex numbers. Now you could take real and imaginary parts and do the same, but that would be extra work. And also for arbitrary fields that you don't have a hope to make it work. So linearity is not the right tactic in this setting. And well, there is a tactic that actually does this. This appeared much later than those tactics, and it's called linear combination. So what happens in here? Well, to prove what linear combination does is looks at the goal. The goal should be an equality. Takes the left-hand side minus the right-hand side equals to 0, and tries to find this A minus 9 in this case as a combination of the left-hand side minus the right-hand sides of the hypothesis you give. But you have to give the linear combination that it is. For instance, here, you see that, well, if you move the 4 to the side here and the 3 to the side here, on the left, you'll have A minus 5B equals something, and for H2, you'll have B plus something equals 0. And then, if you want to do something for A, well, to the first equation, if you add 5 times the second equation, that would do it, right? So that's what linear combination does. You do linear combination H1 plus 5H2, and that solves the goal. Is it clear how this works? Yeah. So you do a linear combination of hypotheses in a weird sense. Okay. Say it again.
Can you perhaps close the interface so it's the algebra?
Yeah, but then you have to believe me when I say it's all fine. But yeah, sure. I'll open it when I need it. Thanks. If I could keep doing like as I did now, right? Oh yeah, with this extension, but I don't have this extension. Yeah. Do you want me to do that? Word. And toggle it. That's it. Oh. Yeah, it's better now? Okay. Oh, I see what happened. Okay, great. So this is linear combination, and yeah, it's quite powerful. So it includes, so it applies ring, of course, at the end. So it takes this linear combination of the hypothesis, right? You take the difference left-hand side minus right-hand side of H1, add 5 times left-hand side minus right-hand side of H2, and then I guess tries to prove that equals a minus 9 in that case by ring. And so at the end there is always a ring application. And so even, I mean, in here, for instance, yeah, well, that's something that you could do in another way, but yeah, just do linear combination H, because H was m minus n equals 0. That would do. For instance, here is another example. So what should I put here? So now you have K is a field. So again, the linearity doesn't have a way to do anything here. It's a characteristic 0 field, and you have S in K, and the assumption is 3S plus 1 equals 4. And I want to deduce that S equals 1. So what I want to do linear combination. And what should I put here? Someone shout out. One-third HS. So that seems to work. Yeah. So you're seeing how it works. Let's do another one.
Excuse me.
Yes.
We have the word back. Can we open the info view again?
Thanks. Yeah. Okay. Oh, my pulse. Okay. Yeah. So here's. Does anyone see the right linear combination? So we want to show 2p6. Yeah, you want to cancel out the 2 q's, right? So if I do h1 plus h2, that should do it, right? Because there is a p on the left, and there is another p on the right, and the 2q adding and subtracting. That was a little more complicated. You have to do something in your head. Now there is all this list of exercises you can try. I don't want to waste time here, but maybe let's do the first one. This one, say, but is this easy? Does anyone see it right away? Yeah, that should be easy. Okay, yeah, great. So you can try them until you get bored. And yeah, well, once you get bored, you go to the next section, which is you can ask Lean to guess it for you, guess this thing for you. Now, there is a tactic called polyrith that's only slightly more than a year ago, and what it does, it's using Python 3 to call Sage online and asking Sage for this, and then getting the results back and suggesting what linear combination should you use. So here is the examples I showed you. So you put by polyrith, and it will say, try this linear combination. You just click, and it keeps working and working, and so on. So that's very nice. It feels like magic, and it's so much fun to do it. You can see that they are all, yeah. Now, oh, one that I could mention to you. This one is quite fun. The linear combination doesn't need to be with natural, well, you saw fractional coefficients. It can be with anything. So here I do a linear combination of, x, y, z, w are complex numbers, and here the linear combination is w h1 plus y h2. That still works. Okay. So Yeah, so Polyrith uses, as I said, Sage Online, and so you need an internet connection to use this tactic. And also, you don't want to leave it in your code, because every time it checks this, it calls Sage Online. So always, here, for instance, you could do bilinear combination, but ring is enough, so it will tell you to just replace with ring. Yeah. So yes, this is a tactic like the one like exact question mark. It's not a tactic you leave on the code. It's a tactic that helps you, gives you suggestion, then you change it into what the suggestion told you. And yeah, so that's the first thing I wanted to show you. And then I will show you ways to use Polyrith the Polyrith tactic, because sometimes it doesn't work on the nose. So let's see. So this file is about well, there is some lemmas about quaternions. First of all, about these Chebyshev polynomials. You probably have seen them. They're defined recursively. Well, this is, sorry, I hope you can read it. T naught is 1, and T1 of x is x. And then there's this recurrence. Tn plus 2 is 2x Tn plus 1 minus Tn. So T2 is 2x squared minus 1, T3 is 4x cubed minus 3x, and so on. So here's the lean definition. You saw already one of these. You haven't seen polynomial rings, but this is what they look like. If you open the namespace so that you can use this notation. So this is a map from the natural numbers to polynomials over Z, and you map 0 to 1, 1 to x, and n plus 2 to 2x plus times t of n plus 1 minus tn. So now, yeah, we have the lemmas. T of 0 is 1, t of 1 is x.
It's some annoying implementation detail in polynomials, and it's contentious among some people, and it's a lot of work to change whether you're forward or not.
Yeah, later on it might complain. Actually, here it's not complaining in here, but it might complain later on, and I don't need to compute anything with it. So yeah. Okay, so for instance, one proof that we want to do, and that I will leave it to you in the exercises, is that this fact that this additivity, well, so the product of two Chebyshev polynomials is another Chebyshev polynomial. Tm times Tm plus k is T2m plus k plus Tk. Okay. So you do induction on M, and here I wrote a proof. I hope you can parse it. You will have time in the exercises, but you want to follow this proof. And the only things that you're using is this T at 2, the recurrence formula, and an inductive hypothesis. So you'll do induction and use these two things repeatedly, but with various arguments. The recurrence, you will use it with different arguments for this n, and the induction hypothesis also you want to use strong induction. You will use it for various arguments, and so here's the skeleton of the proof. Well, you do the 0 and 1 case separately, and then the m plus 2 case you want to use Polyrith. Now, if Polyrith will work if you have the right hypothesis on the context. So you have to put enough hypothesis in the context, which will be related to the induction hypothesis or the T at 2 with certain parameters. Here is placeholder parameters. Now the thing is, you will, when you look at the proof itself, you'll have things like this. You'll want, this is the induction hypothesis. You will want to use it, say, with n plus 37 and k times 37. The thing is, here maybe you want to use this the recurrence for 37 plus m, because that appears in your proof. Now 37 plus m and n plus 37 is the same, but it's not by definition. It's by a theorem, right? Commutativity. And so Polyrith won't detect these two things as the same. This variable, the t37 plus m and tm plus 37 will be different to Polyrith, and so he might not be able to find a right linear combination. So what you do is, after you introduce this hypothesis, so say you have in your context this hypothesis, okay? So here you can see there is a m plus 37 showing, and here there is a 37 plus m plus 2, 37 plus m plus 1, 37 plus m. So to polyrith, these two will be different. And so that will prevent it from finding the right solution. So what you do is normalize all this. So you can do ring NF at all the hypotheses. NF is for non-finishing. You know, if you do ring, it expects to close the goal. If it doesn't, it gives you an error. It's normal form? Okay, yeah, maybe. Maybe it's for normal form. Thing is that this at least it doesn't complain when it doesn't finish. Okay, but maybe it's ring normal form. Yeah. So what it does is it normalizes everything. So at the end, after you see in here now, you can see that in this placeholder application, here I had 37 plus m, here I have 37 plus m again. And here so for instance, say it's 38 plus m. Before it was, before that there was something more complicated. There's 37 plus m plus 1. Okay, so you want to run this before you run polyrith. So hopefully, if you have the right context, then just running polyrith here will close the goal. So that's an exercise. Another one is it's proving this lemma that says that if you have a map from the complex numbers to themselves, which is a real linear isometry, and it fixes 1, then it takes I to itself, and so it would be the identity, or to minus I. Okay, and so here's a proof of it, but and there is a skeleton for the proof, but here is here's the skeleton, and you can try to fill it in. Here is the notation for linear isometry, Li. This is a linear over R. Right? That's a map from C to C, which is a linear isometry over R. And you assume that f of 1 is 1. Then you want to prove that f of I is I or minus I. Okay. And also here there is a double cover of SO3R by the quaternions. So what you do by the unit quaternions? Sorry. So what you do is define a map from the quaternions. Again, this is the quaternions, the real quaternions. They're called H, and this is the way you can send a given quaternion A to a 3x3 matrix, real matrix, and that's the formula. So what this does is deconstructs this A, which is into the real part and the y, z, w components, so the I, j, and k components. And then that's the notation for defining an explicit matrix. So this is by rows. So this would be the first entry, and so on. This would be the first entry, second entry, and so on. So this is the first row, second column entry, and so on. This would be the second row, and this would be the third row. So we'll want to prove properties about this. In particular, we want to prove that if you have a unit quaternion, then it maps to a determinant 1 matrix. Now, because the computations are are quite hard, if you just simply run simp lemmas, if you run simp on statements, it takes forever because it has too much to look. So what Heather did here is selecting a set of lemmas and tagging them with these quaternion simps. And so now when you run simp, you will use these quaternion simps only. And that speeds things up. So here's a list of lemmas that are needed for this to working with quaternions and matrices. And so, for instance, this lemma shows that it's a homomorphism of a monoid homomorphism. That this map that I just defined is a monoid homomorphism, and so you give the map, this quaternion to matrix that I just defined, and you want to show that it maps 1 to 1, and it takes products to products. And so map 1 would be, well, here is the statement I need to prove to matrix 1 equals 1. And so how you do that? Well, so maybe this show here, what it does is it shows something equivalent. Lin detects that this is exactly the same statement as this by definition, but then this way I have it in a nicer way, a nicer form, quaternion to matrix 1, 0, 0, 0. That's how you construct a quaternion. That should be 1 as a matrix. Okay, that's the matrix 1. You see, if I put the cursor here, it tells me that's a 3x3 matrix.
What does this add quaternion sims in the beginning?
Oh, this is tagging. Okay, so I had this attribute quaternion sims for all that list of lemmas. Now I'm just proving a new lemma, and I want that lemma to also be added to that list. So I tag it also as quaternion sims. Usually when you have a lemma, you want to trade the simplifier, you would do add and put here simp, and that would add it to the. Say it again? Oh, but okay, same. Okay, because it's data. So this, because this gives you a map. It gives you directly a map from H to this. So it's giving you this map. So anytime you have a quaternion, you automatically will be able to convert it to a matrix, a 3x3 matrix. Sorry. Yeah, that I'm confused now. Why this is constructing, giving to you. I don't know why you would want to add this. Maybe it's not even needed.
So you put sim on a definition, it being add a lemma that unfolds the definition.
It will unfold that thing, right?
So it's as if you then wrote a lemma like this saying 2 matrix form equals exactly.
Oh, equals this. If you run the simplifier and you have this, then it will unfold automatically, right? Good. So I have to specify. I have to prove these things, and how you prove. So the whole point was to show you how you prove to do these matrix computations using polyrith. So in here, this is a matter of simplifying the definition. So here, I need to. Well, I will want to unfold this to matrix. So when I do X, it's just showing that. How do you show that a matrix? So a matrix, by the way, it's a function of two variables. It takes the row index, that's the first variable, it takes the column index and spits out a number. That's how matrices are implemented. And so X says, well, how you show that two functions are equal if they are equal on any argument. That's the X tactic.
Maybe good to say that X can show this is the tactic to show that any two more complex things are equal by proving the equality of similar.
Of their of how they are constructed, yeah. And for functions, it's what I said. It's f equals g. When you apply x, if you want to prove f equals g and you do x, then you'll have to show that for all x, f of x equals g of x. That's the usual application. And here I do it in the two variables I and j. So after that, I need to show that for all ij, which are just numbers. So fin3 is a type of sets of three. It's a set of three elements, 0, 1, 2, and so I and j are numbers between 0 and 2 included. And I want to show that when I apply the left-hand side to ij, I get this 1 applied to I and j, which is just 1. Sorry, this is the matrix 1 applied to ij, which will be either 0 or 1 depending on whether I and j are equal or not. And so I do a fin cases that it's proved by cases, by which case, but what can be I or what can be j. So that's what these two instructions do here. And so maybe I should first do it. If I do fin cases I here, I think it's busily processing or something. Yeah.
If you write hash exit,
Say again?
If you write hash exit immediately after that, then it won't try and load anything further down.
Oh, okay, it's fine. So here you see, fin cases I give me 3 goals. That's when I is 0. You can see the 0 somewhere, and there's no, and then the case where I is 1, and the case where I is 2. You can see 1s and 2s somewhere there, and then for each of the cases, so for each of these 3 cases, I would like to do the case where j is 0, j is 1, j is 2. And so each case would split into 3, and I with 9 cases at the end. So you do that when you want to apply a tactic to all the goals at once. You do this semicolon with brackets, with angle brackets, and so that the next tactic will apply to all the goals. So when I do fin cases j, now I'll end up with 9 goals. Right? When it finishes, that's why I warned you that this is heavy computation at some point. Now, these 9 goals, yeah, now each of the goals corresponds to one of the matrix entries. And how you solve each of them, well, you just do simplify, you check the definitions, and they will work. There's no computation to be done. So that's why this sim quaternion sims works. So all of them get solved by the same sim quaternion sims. That's why if I put here all the goals, use the tactic sim quaternion sims. Now, maybe for the lean experts, maybe I can get some help here. Importing, that's the only thing I could make work. In lean 3, there was sim could be called with a width parameter, and here I would have said sim with quaternion sims, but as I did then. Yeah, so that I did the right thing, but this is not documented. I couldn't find the documentation for this, so but yeah. So okay, got lucky then. Yeah. Okay, so same mapmul does the same here. I want to show that the quaternion to matrix of the product is the product of the matrices, and yeah, it just simplifying as well. So this is how you would do a. But now, once you simplify, you get things like that. See, you get the explicit expression for each of the matrix terms of the matrix entries. And you see, this is just a complicated algebraic expressions, and they all happen to be solvable by ring. There is no hypothesis that I need to deal with. This is directly just by manipulation. So this would be very tedious to do by hand, and Lean does it very easily. Just call the ring tactic in all these 9 goals at once, and they just work. Okay. Now ring something that won't suffice. So here is the definition of the unit quaternions. It's a submonoid. Well, it's a subgroup, but in here it's only submonoid. In the exercise I added the exercise to prove that it's actually a subgroup, but it's defined to be those quaternions whose norm is the kernel of the norm square map. Okay, take the norm square to the reals and the ones that give you 1. And here's a theorem that says that an element is in the unit quaternions even only if, well, if A is x plus I yi plus z j plus wk, then you expect that x squared plus, well, it's in the unit quaternions even only if x squared plus y squared plus z squared plus w squared is 1, which is what this is saying. Okay, and this is just by definition, so you simplify that and you're done. So once you have that, then you can try to as I said, prove that they make a subgroup. So you have to prove that they are close on their products, and 1 is there, and using Polyridich shouldn't be too hard, and by inverses. Okay, so I gave you a little hint here, but you can do. This is not used later on, but it's good to know, and it would be nice to have it added to Mathlib. It's not in Mathlib. So now, for instance, let's prove that if you have a unit quaternion A, then when you look at the matrix corresponding to it, it's an orthogonal matrix. Okay, and so So that's the context. And so you unfold the definition. It means that A times, it's star is 1. And well, you can destruct A and have X all the components X, Y, Z, W. And so, well, we would like to do, as before, an xij and thin cases, and then check all the terms. I will have this in my context. I'll record the fact that x squared plus y squared plus z squared plus w squared is 1, which I know by the lemma I had before. And then, as before, I do all the cases and do quaternion sims. And you see now I get these expressions. Now these expressions are not, so you see the first one should be 1, the second one should be 0, because so the diagonal entry should be 1, then off diagonal should be zeros. So the first is 1, 0, 0, and then 0, 1, 0, and so on. There's 9 entries. Now if I try a ring on here, it would fail because they are not equal to 0 on the nose. I need to use somewhere that x squared plus y squared plus z squared plus w squared is 1. And so here's when I can call polyrith in each of them. And you see all of them have worked, and it gives me different combinations of my hypothesis, which I think, yeah, that's kind of slow to update to the next one. Yeah, they run all of them. Yeah, eventually works. Okay, yeah, so you can click later on, but each of them gets solved by a different linear combination, and did it yet? Well, so that's. But yeah, it's important. If I simply remove this from the context, you will see it failing. Hopefully, well, I'll get back to this, but you'll see it failing later on. So here, this is just restricting to the unit quaternions, and maybe well, you can look at. Yeah, here we check the double cover, but here you see in the here this is another exercise I give to you. Again, you want to check that you have this double cover property, and so that your goal, yeah, it means that the kernel of this matrix home that you defined is just plus minus 1. That's what you would like to show, and so while you simplify as before, you get concrete examples. So now. So here's the goal that you have now. This complicated matrix is 1 if and only if x equals 1, y 0, z 0, w 0, or x minus 1. So if and only if the quaternion was the 1 quaternion or the minus 1 quaternion. Yes, and how you do that? Well, it's an if and only if, so you have to split into the 2 directions, and in the hard direction, it's the right direction. Yeah, you have this complicated thing in the context, right? That's lots of these are 9 equalities really, and then using these 9 equalities, you want to deduce either that y z and w are 0, and then that x is 1 or minus 1, and so. Well, I would like to show first that y is 0, and that simply doesn't work by polyrith automatically because I need the particular matrix entries in the context. Polyrith can't work with matrices. So, for instance, here H00 is exactly this looks, it's this conf-func tool that takes this. Remember, matrices are like functions of 2 variables. And so this says that just look at the 0, 0 term of the matrix. of this H1, of the equality that this H1 represents. And so when I simplify it, I get H00 says that the first entry is 1 in the matrix. Okay, so if I add enough of these halves, I guess I could get, if I put all the 9 halves here for all the entries in the matrix, simplify all of them, so I get these simple expressions in each of them. Some of them will be 1, some of them will be 0. Then this will be doable by polyrith. All these y and z to be and w be 0 will be doable by polyrith. And then I'll get that x squared is 1 squared, really, by polyrith as well. This even is independent of the others, so I have it already. And once I have that y and z and w are 0 and x squared is 1, then it will be very easy to show that x is 1 or minus 1. Right? And the easy direction is just simplifying. So I do it for you. I don't know how much time do I have left. Not much. Nothing. Okay, so there's 2 more files. I can say what they are, and then you can try them on the exercises. This is studying curves, and here the problem that you will face is something like this. I mean, this is the simplest instance. You want to show that x is 2 from these called x is a rational number, say, and you want to show that from x squared minus 4x equals minus 4, then x is 2. Now, if you move the minus 4 to the right, you can factor it out, and you get x minus 2 squared. So x minus 2 squared is 0, and so x minus 2 should be 0, x should be 2. But this right-hand side is not a linear combination really of the left-hand side. And so what you do is first show x minus 2 squared is 0. That you can do by polyrith. And then you apply pow equals 0, which says that if x to the n is 0, then x equals 0. So sometimes you have to help polyrith in this way, right? So that's because the ideal, if you know algebra, the ideal that these hypotheses generate is not radical, and your goal is in the radical of the ideal, but it's not in the ideal. Yes. Here is another instance where this fails. Here you have 2. Well, you do control. Yeah, you need to cancel. So here you want to show that s is 2. Sorry, s is minus 2. And what you can prove is that r minus 1 times s plus 2 is 0. So that, and then adding the hypothesis that r is not 1, then you would be able to prove that s is minus 2. So you see, when you run contrapose, so it's just by contradiction, and you can show that r is 1 by polyrith, and then and here you see now you now have that r minus 1 is not 0. Now this says that if you want to cancel this 8, you can cancel some thing on some term like a, and so you apply it with hr prime, and the goal will become this more complicated appearing goal with an r minus 1 factor, and this is a linear combination of the hypothesis. So polyrith will work in this case. Whereas if I hadn't added this extra factor, then polyrith would not work. Again, that's because your ideal is not is the product of 2 ideals, and your element is in one of them and not in the part. So again, that's something that you have to fight manually. And yeah, that's it. There is another file you can try on the exercises. So where now you use a tactic that I didn't talk about, which is called field simp, which clears denominators. When you are working over a field, you have denominators. It clears them out if you have in the hypothesis the fact that they are non-zero. So if you have zero denominators, it takes them out. And so that's good to combine with polyrith as well. So here you can see examples of it running at the beginning. So maybe I end with this. Here you are assuming b is a squared plus 3a, and you want to show b over a minus a is 3, and a is non-zero, of course, otherwise it doesn't make sense. And here, if you just do polyrhyth at the beginning, it won't work. But yeah, it won't work. But if you do fill simp, what it changes the goal into you see, move the a to the other side, and that's something that polyrhyth can deal with. So yeah. So the idea is, yeah, put enough context or modify the goal so that polyrhyth just does a simple computation for you. That's the idea.